So welcome back everyone, this is Advanced SQL Chapter 7. And what we will do is continue our tour through PL SQL, the procedural SQL extension that you will find in many relational database systems. We've said that PL SQL is special in comparison to other scripting or imperative programming languages because it's just tighter integrated with the rest of the relational system. And I think that becomes most apparent when we are looking at expressions. Okay, so that would be, of course, one of the core constructs in an imperative language, the expressions and statements. We will look at both, but let's look at expressions first. And what we will find there is actually that expressions in PL SQL are just SQL expressions. Any expression E that you could write in a select clause, for example, okay, would also make for a syntactically correct PL SQL expression. So SQL and PL SQL share their expression language. And well, that of course leads to a perfect match between the operators and functions that are supported, the syntax that is supported, and the types that are being supported. All right. Okay, so in fact, if you write PL SQL expressions like these, and we will have a closer look at these, then what you will find is that there are embedded expressions in there. So that expression E here would be such an embedded expression, the right-hand side of a variable assignment. And well, this predicate, this inside the conditional here, the if-then-else conditional, which will behave exactly as you would expect it in other procedural languages. Well, this expression here, the conditional, would also be a regular SQL expression, one that would probably return a Boolean, so that the types match here. Okay. In fact, what you will find if you look behind the curtains of the implementation of the PL SQL system inside PostgreSQL, you will find that the evaluation of such an embedded SQL expression here would just lead to the evaluation of this particular mini SQL statement that is being issued by the PL SQL interpreter. So the context switches from PL SQL for the brief moment where we will invoke SQL to perform this computation for us. We will receive a value, and with that value, with this expression value, the PL SQL interpreter will continue its computation. So that, of course, leads to a very close interoperability between PL SQL and SQL. What we have known to work so far in the SQL context will continue to work in the PL SQL context. There is, of course, a performance impact because we have to switch context. We have been in the imperative procedural statement by statement PL SQL context, and we now have to temporarily switch to the evaluation of SQL expressions again. So that means that control is being passed to the SQL subsystem, which will do its thing, evaluate expression E. Then the value is passed back to the PL SQL system, which will then resume its evaluation of the PL SQL program. All of this requires context switches between these two language subsystems inside the RDBMS. And there's some friction there. There's a performance penalty that you can observe, and the very last slides in this particular chapter, chapter 7, will pick this up again and try to quantify and highlight what these context switches between PL SQL and SQL really could mean. To alleviate the whole thing and to make this performance penalty less significant, well, PL SQL plays a number of tricks. So if you see that one expression, the expression E that we were talking about, that is actually an expression that is containing 3 variables. So expression E refers to variables that are in scope. Then what you will find is that the system will compile this expression E. It will ask the SQL subsystem to compile the expression E to bring it into its internal format that can be evaluated quickly, and that the 3 variables x and y in this particular example are like holes in that particular compilation, in that particular plan that is being produced by the SQL subsystem. So the actual plan is compiled once. The holes x and y are being filled with their actual bound variable values at the time when expression E is being evaluated. E might be evaluated many times for many different bindings of x and y. What the system will then do is reuse the compiled expression E, just plug in the values x and y, and thus gain some performance advantage there. And I think we can even see that or see the idea behind this if we switch over to the terminal in just a few minutes. All right, so that would be PL SQL expressions, which are just SQL expressions actually. All right, so we have seen one of these, one of the PL SQL statements, the very basic assignment statement already on the previous slide. And here's the assignment statement again. It's using this colon equals syntax just to tell it apart from just the equal sign, which is still used for comparisons. All right, so if we evaluate such expressions here, then E has to evaluate to a single scalar value. Well, it has to evaluate to a single value that could be a scalar or a row or an array or some user-defined type, of course including null, but it has to be a value that can live inside the single cell of a relational table. And well, it's exactly these types of values that can live in a table cell. We have talked about this many times. This is a restriction on E. Variable v may not be table valued. In fact, E may not be table valued. So E may only evaluate to a cell value, which is then assigned to a variable v of the correct type. If the type of E and the declared type of v do not match perfectly, well, then the system tries to cast the value of the expression to the value of the variable, if this is possible at all. Of course, this may fail at runtime. We have talked about the casting rules and the effort that SQL invests in casting values at runtime at the beginning of this course. Exactly this is what happens in the context of assignment statements. Of course, you may use all the syntax that you are used to in the SQL context to formulate your expressions E. You may use the textual literal syntax that we have used to express complex types like JSON, geometric objects like points or arrays. All of these syntactic specificities, of course, apply also to E. So you will find yourself to be using familiar SQL syntax to formulate these expressions E. Once the evaluation has happened, once the casting has happened, if it's necessary at all, of course, variable v is bound to the value. In all subsequent statements, v will have that particular value unless it is overwritten. So we are talking about a real imperative programming language in which execution happens state by state and variables may change values, may be assigned multiple times. For example, in the course of an iterated computation, for example. Okay, so let's quickly switch over to the PL SQL terminal. In this case, it's a real PL SQL session that we are driving here. So here we go. Well, I've prepared a sample UDF here, a sample UDF named x per expression, because the focus is on expression evaluation here. We will pass in a single parameter of type integer called x. All right. We've got some local variables in the block in the body of our expression function, and the local variables x, s, p, and q are declared here with their types, but unassigned at this particular point. So all of these would be assigned the value null of their respective declared type. All right, to change that, we will perform assignment statements. From top to bottom here, there is a sequential execution order in these UDFs, or in these code blocks. Well, xs will be an array just as declared, an array of integers, and x will fit right in there. X is an integer. That will be a homogeneous array of integers that we can assign to xs. We can use the textual literal syntax to specify points, for example. So we're using that here. round parentheses, two x and y values make up a point. This literal string will be casted to the type of the variable on the left hand side. The type is point. The cast of this particular literal value to point will succeed. P will be a point of coordinates 0, 0. We can of course use the constructor syntax to construct points here. So Q will be a second point that has been assigned, well, x value 20 and y value x here, as we pick the corresponding elements from the access array. All right, and well, then just to return the function, we will evaluate this particular expression. It's an expression, as you can see, that has two free variables, p and q here. So such an expanded expression, as I told you, will be compiled once by the system. P and q as the free variables will be holes in that particular expression. And well, if we evaluate this function, the expression function once again, the compiled expression for this particular return expression, it will be reused, and the current values of p and q will be plugged into the holes to make up an expression that can then be evaluated. All right. Of course, because the return type of the expression function that we are defining is int, and because this will lead to a float value, there will be some casting going on that will turn this float value into a return value that is of the declared return type. All right, and we can see that. Let's define the function first. All right, there it is. And we can see that if we pass in the arguments 37, so x is 37, that means that xs2 here, the second array element, is 37. This leads to a point that lives at coordinates 20, 37, and if we compute the distance here, this is the point distance operator, then that will lead to a fractional distance, but as you can see, casting leads to an integer result when we evaluate our expression function. All right, okay. So just to demonstrate what it means to compile an expression once and leave holes in it, I would like to point you to maybe lesser known SQL statements that have been available in PostgreSQL and in other RDBMS under similar names all of the time, but we haven't used these yet. And it's actually the prepare construct in SQL. Prepare construct indeed lets you compile a particular SQL query. In this case, it's a very simple select clause only, but a arbitrarily complex query could be placed here, inside this prepare expression. We name that expression, and we name the holes in this expression by $1 and $2 here. These would be the holes in the expression. We cannot evaluate this expression or this entire query unless the holes are filled. The holes are of type point and point. So these would be the types of the expressions of the holes of $1 and $2. So that would be a compiled expression that is waiting for evaluation. We can evaluate it later by referring to its name, expression1 here. This is a user-defined name. All right. And when we refer to this expression, which we do here, pass in values for all the required holes. So in this case, it's just the point 0, 0 and 20, 37, just the 2 points P and Q that we have seen in our UDF above. Well, of course, the holes would be plugged, the evaluation would be performed, and we would obtain a result. And that result would be the result of this particular execute SQL statement. All right. Well, once we are done with this particular expression and we do not plan to invoke it further, we can just deallocate it and throw away the prepared plan that has been prepared in the background. So if you know that there are queries that will be, or expression that will be evaluated again and again with different parameter values or hole values, then such a prepare and execute pair could be the way to go. You will save repeated query compilation, preparation, and optimization. So let's see whether this works. Let's prepare this name statement with 2 holes. Okay, has been done. And now we could execute it with particular values for the two holes and receive this distance between the 2 points. Indeed, it's a fractional distance, and now we can see that indeed at this particular point some casting to type int has been performed. All right. Now that we don't need this expression anymore because we have invoked it many times, million times maybe, we can deallocate it and get rid of it. All right, so this planned preparation and then instantiation evaluation process is exactly what happens when PL SQL interoperates with SQL expressions. All right. So we've talked about the assignment. We have talked about the assignment of expression values to variables here. This comes in a different syntactic form too in PL SQL. All right. So this is a particular SQL statement that can be used and as a statement in a PL SQL UDF. All right. So that would be, this SQL query would be a statement inside a PL SQL UDF, and it will be an assignment statement. You can see that this normal SQL query has been augmented with this into clause, right? And the semantics of this statement are: evaluate the SQL query as usual, all right? This select clause will construct a row of n fields. This row will be assigned to PL SQL variable v. All right, so it's just an assignment statement that assigns this row value to variable v. Of course, the declared type of v and the number of fields and types of the fields in the SQL expression has to match. All right, if you were to get hold of the different fields in separate individual variables, you can use this variant syntax in which variable vi will receive the value of expression ey. So you deconstruct the constructed row value in one go and have access to the individual fields in n different PL SQL variables here. Excuse me. All right. So this is what has been described here in these points 1 and 2. There's a possibility that indeed this particular query will yield no row at all. No row at all. All right. Well, then the value of v will be null. Okay. And there will be an indicator variable that is maintained by the system that will indicate that there is indeed no row that could be assigned to your variables. All right, so the found variable would be set to false. In the other case, where there is indeed a result that has been returned by the query, found will be true. So what you will often see is a sequence of statements where you use this select statement to receive the result value of this particular query and assign it to v, and then a conditional statement that would check the found variable just to see whether the evaluation of the query yielded some results or not. And this probably would prompt your UDF to take either one or the other path of flow of control inside your UDF. All right. This is one case that should be considered, the returning no row. What would be the case if there are many rows returned from this select query here? Which row would be assigned to v? Well, the answer is that the first row would be picked. As you know that there is no first row normally in such a SQL query unless the order has been properly defined by order by. Well, then some row will be picked, which is of course horrendous. So please make sure to either formulate queries that yield a single row or maybe no row, or that yield a result that is deterministically ordered. Okay. If you really want to make sure that your queries do not return more than one row, and I think that would be good practice, Then there is the into strict variant of the into keyword that would enforce single row query results. So on the occasion that more than one row is being returned by this query here, you would get a runtime error. And I think at least for development purposes, that would be a good indicator that something is going wrong with your queries here. Okay, so that would be one way to communicate query results back to PL SQL variables. Let's see how that indeed works in the terminal. So that would be one example of a select into statement that we are using inside the UDF. That UDF is the max A for B UDF. So well, the name says it all. We want to find the maximum A value for a given B value. So that what you would receive as a parameter here. In this function, you would receive a B value. Our task is to find the maximum A value for this given B value. As you see, well, we will perform our search for that A value inside our playground table T. And that explains the type annotations that you will find here. All right. Of course, we will pass in the B value that is compatible with the B column of our T table. And since we return the maximum A value, we will return a value of a type that is compatible with the A column of our T table. All right. So, well, this is a very, very simple function. We would just use a select query like this that would indeed be on the lookout for this particular maximum A value. Well, this query is written in a somewhat convoluted style, but it just fulfills its purpose. It will order the result of the T rows that of course match the supplied B value. It will order them by ascending A values, by descending A values, and then pick the first, so the largest one. And this is exactly the value that will be returned here at this particular point. What you can see here is this particular syntax that I'm using to disambiguate the reference to value B. Just writing B here would be ambiguous. It could refer to the B column value of table T. It could also refer to the B argument of our UDF. Well, to disambiguate this, let's just use the name of the UDF as a prefix, the implicit block label that has been assigned to this top level block inside our UDF to unambiguously refer to the correct B here, the argument B. All right. So what could happen now is that there is indeed no such B value inside our T table. And as such, well, this would deliver no row, and there would be no row that could be assigned, no A value that could be assigned to our PL SQL variable here. Okay, so this case could be detected by using, well, the system maintained not found variable. All right, should that test not found yield true, so if found is false, then well, we supply a default A value in this particular case, right, which is then being returned. All right, so I think all of this should be pretty obvious. Note that max A here and the assigned 0 will be casted to the correct return type. So that will be a 0 of the return type, of the numeric return type, and that's in that case that would fit the A column of our T table. All right, so if we compile that, then you can see that indeed the system is aware that the B column and the A column of our T table have particular types, and they are being used to instantiate this UDF for us. All right. And well, we can then invoke our max A for B function. Indeed, we invoke it 3 times here for different B values x, y, which I think indeed occur in table T, and this questionable question mark value, which does not occur. So we expect the default value 0 to be returned in this particular case. So the not found will probably be satisfied here in this third call of our UDF. Evaluate that, and that's what we see. Maximum value of A is 5, 4, or default 0 in this particular case. So that would be select into, receive the value of a query and place it into a PL SQL variable. Okay, there is one alternative syntax that you will often find in PL SQL scripts that is applicable to situations where I would like to receive the single return value, a single scalar or cell value that a query is returning, and assign that to a PL SQL variable. I could use the select into syntax. I could use this alternative syntax. Since we know that the right-hand side of such an assignment statement, this right-hand side here, is just being placed in the context of a normal select here, well, we can make use of that. We know how these select statements with subqueries, of course with scalar subqueries, are being evaluated. Nothing else but the scalar subquery can be placed inside a select clause here. Okay, so what we expect this query Q to return is indeed a single cell, single row value, something like this. And as expected, that C value in a scalar context, or in the context of this assignment here, that is asking for a single cell value, in such a context, value C will be extracted and then assigned to variable V. All right, this is what's written down here. Well, if there is no row being returned by query Q, then null will be assigned to our variable V. Okay, but if there is more than one row returned by Q, since this is being used in a scalar context, we will receive we will receive the regular runtime error that we know from our discussion of SQL. And this is just what's described here. Please note that in this particular case, for example, in this case, variable found is not being set to false here. All right, so this is something that is bound to the into construct. It's not being found is not being maintained and set if we use this alternative syntax to extract the cell value from query Q. Still, it's a very natural and very nice syntax. I can use and write Q as I always would. I can use assignment statements and not resort to the into keyword. So this is a style of assignment that is preferred by many PL SQL developers. All right. Right. So that would be expressions, assignment, and the interoperation between PL SQL and SQL to evaluate embedded SQL expressions, which are just SQL expressions, no excuses here. But there is some friction, there is some performance penalty. PL SQL to SQL and back has to be performed. As I told you, we will look at the performance consequences a bit later on. All right, so much for this portion of PL SQL discussion. There's more stuff to be discussed. This is material for the upcoming videos. Stick around. Bye-bye.